Welcome to this recording of statistical modeling. In this video, we're going to talk about the geometry of least squares and define some important quantities that will be used throughout to perform model diagnostic. Okay, so it's math heavy. The purpose is not to draw you with formulas, but rather these formulas exist, the efficient way of computing things, and a lot of the elements that we'll be investigating to check the goodness of fit are constructed based on some properties of least squares. And so, unfortunately, we have to introduce some of those quantities. So this is somehow optional material, but I will be referencing later on some of these terms. Okay, so we start with the model equation, right? This is a statistical model. So there are two ingredients to a statistical model. The first is an expression for the average of the response as a function of potential explanatories and parameters. And in a linear model, you assume that it's basically for every observation, I have a vector p plus one vector, so an intercept plus p covariates. I have a vector, I assign weights beta, and that gives me a linear combination of these, gives me the average for that observation. Okay. On top of that, I assume that I have an additive error decomposition. So not all observations follow exactly the model. There is random variability even if the model holds true. And I add this error term. Okay. And I suppose that the error term has mean 0. That's equivalent to saying y as average x beta. Okay. Or if you want, it's some mean. Okay. And I assume that observations are at least uncorrelated with equal variance. So if you look at this model, of course, this was the model that generated data, you generate n epsilons. You have the unknown betas, you have the unknown sigma square, and somehow it gives you observations, and that's the bottom decomposition. I know the observations, I have n of them, but there are more unknowns than known things. So what I can hope to retrieve is not the errors, but rather estimate the parameters and try to retrieve some sort of ersatz of these. So I'll have a decomposition in terms of observation equals fitted value plus residuals. The fitted value, that's x times beta hat. Okay, so I go in the equation above, I replace beta by beta hat, and then I define the residual as observation minus the fitted value. Okay, so let's dig a bit closer into what are the fitted values. Okay, before we begin, some geometry. So what am I doing? Essentially, I said I'm just assigning weights to every observations and I'm adding them up. Now, if you consider observations as column vectors, residuals, observations, fitted values, and so on as n column vectors, and the same for the matrix, the model matrix X, what I'm considering here are linear combinations. Okay, so my model matrix generates a column space, and I can look at any potential combination of these. Okay, so I'm defining this because I'm going to illustrate it in the next slide. I said my fitted values, that's the model matrix times my beta hat, my ordinary least squares estimator. And if you expand the formula for OLS, what you will find out is that this can be written as x. So x is n times p plus 1. X transpose x is p plus 1 square. Okay, you invert this times p plus 1 times n. I get a matrix, which I'll call h of x, h for hat, and x to indicate that it's associated to this model matrix. Okay, so I get that the fitted value are equal to some matrix that puts a hat on y, hence the name hat matrix. And this n by n square matrix is a projection matrix. Okay, and projection matrix have particular properties. It's, of course, it's a symmetric matrix. So if you take its transpose, you get the back the same thing. And if you hit h of x times x, it projects onto the space. So what does it mean? Let me show you a picture in 3D, because I cannot, consider the case for 3D and imagine extending this. These are vectors in Rn, and the span is in p+1, okay? Arbitrary dimension. But what happens? What happens is you said the true mean is a linear combinations of the x. So it lies in the vector in the column space generated by your model matrix somehow. Now you know no beta. So it's some value, the dashed line, the dashed blue, and then there's some error term that gets added, and what you see is y. Okay, this vector of observations. Now, what will you do? Well, we've said the fitted values are the projection onto the span. So essentially what I'm doing, I have the vector, I have the plane, and I'm looking at the parameters that, linear combination that minimizes the error. And what is that? Well, it turns out that this is the shadow. Okay. When I do this orthogonal projection, what am I doing? Essentially, I'm constructing two vectors that are perpendicular to one another. One is y hat, and the other is E for the ordinary. E is ordinary residuals. Okay. So in 2D, that's the equivalent of being of creating a right angle triangle, y hat, and E. Okay. You can notice y hat and E are different from x beta and epsilon. That's normal. Okay. So this orthogonal projection matrix, I'm not interested so much in the property, but just to show you, these two decompositions are different. Okay. But because my residual is orthogonal, right, to the span of x, there are some important properties that I can use for model diagnostic. What are they? Well, because they're orthogonal, their inner product is 0. And if you actually look at the definition of sample correlation, it's an inner product between two vectors. That means that they are uncorrelated. Okay. To show you this, I fit a model to the college data on gender inequality. Okay. I obtain the residuals. I compute line 6 correlation between residuals and fitted value. I get up to, my computer precision 0. If I hit any column of x with E, because E is orthogonal to the whole plane, the whole span of x, they also are uncorrelated. Okay. That also means one of the columns of x, or a linear combination, so typically you always include an intercept or something equivalent. Why is that? Because if I do this, the sample mean of the residuals is 0. Now, if you go back to the first slide, okay, I've said we assume that the random errors have mean 0. And here, okay, so they had theoretical mean 0. What am I going to do to emulate that? Well, I'm going to force the residuals to have sample mean 0. Okay, so as to mimic the model I've considered. That's why you put an intercept. Okay, it doesn't have to be an intercept because we'll see later, anything that's equivalent generates the same predicted values, and so same orthogonality. Okay, so why is this useful? Well, if I make plots of the ordinary residuals E against fitted values or columns of X, so here I'm taking years of service, and I fit a simple linear regression, right? So this is a bivariate scatter plot, y hat versus E, or X, here service versus E, and I fit a straight line. Well, they're uncorrelated, so the best fitting line has slope 0. And there is no residual linear dependence between those two. Now, because I have added an intercept, sorry, the residual also have mean 0. So not only is the slope 0, the intercept is 0 for all those panels. And that's useful to detect forgotten interaction, nonlinear terms, any local dependency that would not have been captured by my model. This could be potentially picked up from the residuals. So that's a useful graphical diagnostic. Second important properties of or corollary of this notion of linear span, etc. As long as so if I fit two models, okay, potentially different explanatories, if they generate the same linear span, they generate the same prediction, the same fitted values, the same residuals. Here's a demonstration. I'm going to fit a model. So the default model, which I'm not showing here, is sex plus field plus rank plus service. And you can see the model matrix here on lines 7 to 10. I have the intercept. I have a dummy for woman. I have the field, okay, 0 for applied, 1 for theoretical, and so on. Now I'm going to modify this ever so slightly. I'm going to remove the intercept. So instead of having a column of ones, I now have a column of indicator dummies for both men and women. Okay, so now I have 2 dummies instead of 1 for women. But of course, if I sum those 2, I get back a column of 1. So they're linearly equivalent. I can also use a sum to 0 parameterization for the contrast for the rank. That's also equivalent up to linear transformations. I can scale variables to have sample mean 0 and unit standard deviation. That's service here. Now service here is in year. Now this is in terms of standard deviations apart from the global average at 0. These are, linearly equivalent. They generate the same span because these are all linear transformation of columns, combinations of column. And so when I fit both models and I look at their fitted values, their predictions, you can see line 17, I check, is it true that they're equal? Both are them are, and it is indeed the case. So that's quite useful. Of course, the parameterization, changes the coefficient, so it changes your interpretation, but that means you can, rescale variable to have mean 0 to make things more interpretable, notably your intercept. You can scale variables to facilitate sometimes other things. Okay, so you could scale all variables to have mean 0, variance 1. This is a linear transformation, and so it doesn't affect the fit, which is good. Okay, let's go back to the residual. I've defined the residuals, E as being, y minus y hat. Y hat is h of x minus h of x times y. And so residuals E here are, E is identity minus h of x. Okay. And if I assume that yi is normal with mean xi beta and variance sigma square, I can show that ei marginally, so if I just take a single line, it's going to be also normal because linear combinations of normal and convolutions are also normal. It's going to have mean 0, which is what I wanted. That was what my error terms had. But annoyingly, I get sigma squared times 1 minus HII. And the HII are the diagonal elements that I'm going to call leverage later. These are the diagonal elements of the hat matrix. And these HII are not the same. And so that means that the residuals have different variance. The second consequence, identity minus h of x. So h of x is rank p plus 1. Identity minus h of x is also a projection matrix. It has rank n minus p minus 1. And there are n observations. If the rank is n minus p minus 1, that means there are p plus 1 linear relations between them. Okay, so truly I have correlation between the observations. And if you do the math and you look at the covariance, you'll find that the covariance is minus sigma squared times hij. So again, depends on the elements of this weird matrix. But the residuals are correlated. So I could, extract. So there's two things you could look if you wanted to look at residuals. And why am I looking at this? But essentially, if I want to diagnose something and look at the goodness of fit. So normality assumption, I can make QQ plots of this. If I want to get standardized quantity that all have the same variability, that's also useful for other purposes. I'm going to have to standardize my errors so that they have mean zero and unit variance. Okay, so I'm going to estimate sigma square, and somehow I'm going to extract the HIA. Okay, so you could extract n minus p minus 1 linearly independent residuals, or you can standardize these residuals to have the same distribution, but keep the linear dependence. Okay, there's no getting around. As n grows larger, typically Hij becomes, small, and so this kind of becomes less of an issue. So I want to standardize my residual to have mean zero and unit variance. The mean is easy because the theoretical mean is zero, so I'm not going to do anything about it. The formula says that the variance is sigma squared times 1 minus HI. H, I know, that's just a function of my model matrix, but sigma square I have to estimate. Normally, what do we do? Well, we compute S square, right? S square is the sum of square error divided by number of observation minus number of parameters. Now, if you stare at the formula, you'll notice that the residual I want to standardize appears in the formula for the variance. So if I use this formula, somehow the numerator and the denominator, right, E divided by its standard deviation, they're going to be correlated. I'm going to introduce dependence. That's not what I want. So what am I going to do? Well, I'm going to cheat. I'm going to say, well, I have an unbiased estimator of the variance. The only problem is that EI is related to the rest. Okay, why? Because I'm using this observation twice. Well, I'm just going to refit the model without that observation. So you remove line I, you fit a linear regression to n minus 1 observations. You get the estimated standard deviation, S minus I, which I'm not consistently labeling here. Okay, so it should be S minus I. They're all the same. So this and this are the same. Okay, up to square. And because, if I assume that the observations are independent, if I fit the variance based on these observations and I just standardize this residual, these are also independent. They're based on independent data. Of course, I'm not going to refit a linear regression. Okay, that would be quite costly. Thankfully, you can do some math and show that actually there's an explicit formula for the variance of the linear regression in which you've removed observation I, and it can be expressed in terms of the variance our empirical variance, we've already estimated that, the I residual, and again, this HII term. So now I have a formula. Good. I can take the square root of that. That's going to give me an estimated standard deviation. I can standardize the residuals, and I'm going to get this Ri, which I'm going to call the jackknife. Okay, so removing one observation at a time is a technique called the jackknife. And so these are called jackknife or externally studentized residuals. Okay. In R, you type R student of a linear model, and it's going to spit out these values, okay, using the formula. So you don't need to know the formulas. You don't need to know the elements. It's just these residuals have been constructed in such a way that they are not independent because they have linear relations between them. But marginally, everyone has a student, every of the point has a student distribution, okay? So that's already more useful for a QQ plot because they all have the same reference to which you can compare. Let's dig into even furthermore into this hat matrix. So if I look at the diagonal element, I can go back and think, well, I express y hat as being h times y. Okay, h is a matrix, y is a vector. So if I look at y hat, I basically take the row of that H matrix, I multiply by the sum of all the y's, and that's just the linear combinations of the y. Okay, so I'm somehow assigning a weight to every observation, and I'm computing a weighted average, and that gives me my prediction of the observation, which is not the same as the observation. So the hat matrix, if I compute the partial derivative of that linear prediction as a function of, how much of the fit of observation I was impacted by the actual observation you had. Okay, I'm going to retrieve HI. And so HI represents the leverage of an observation, how much it affects the fit of itself. Properties of projection matrices tell me that the elements HI, they're diagonal elements, they are bounded below by 1 over the sample size, 1 over n, and bounded above by 1, okay? And the sum of the leverage, that's the rank of the matrix, so that's p plus 1. And if my design is good and every point contributes equally and fairly to the regression, on average, they should thus have, a sum of p plus 1 divided by n. That's a good design. Now, they can be anything between 1 over n and 1, as long as they sum to p plus 1. So what we're going to look at is, okay, what are the points that are influential? Which ones affect the fit most? I'm going to show you pictures in a moment. But essentially, we're going to see points that have a high leverage. Typically, these are ones that have unusual combination of explanatories. Okay, either you have, say, years of service, there's a bunch of years of service, everyone pretty much has less than 25 years, and suddenly you have someone who's 60 years of service. That one might have a high leverage. Or it's unusual combinations of variables, okay? For example, someone who has a lot of years of service, but very few years since PhD, whereas for most of them, this was highly correlated. So these combinations kind of affect the fit. Also depends on what you have in a model, what are any interaction, blah, blah, blah. One condition for my model estimator to retrieve is that no point dominates, okay? So I have some uniform convergence. All the points, no points is gonna matter. The more observations I gather, every observation somehow, even the large ones, should contribute more or less equally. In other words, even if I have some very influential points, as I gather more data, their impact is going to decrease, okay? If a point drives the whole fit, then that's no good. I'm getting sort of rubbish estimates. Okay, let's look at some pictures. And let's make a distinction now between influential observations and outliers. The formal definition of outliers, I'm not going to get into this. Essentially, an influential observation, I've said this is one that has an unusual X value. Okay, so unusual explanatories, typically far from their overall mean, and that's the mean in sort of multi-dimensional sense. So on the right panel, you can see this observation here with my cursor is very far from the rest. And so when I'm, plotting the line, well, it's going to pull it towards itself more than the observations here where there are other points that are kind of pulling apart. Okay, so really think about the leverage. It's how much is it affecting if every observation has a little spring. Of course, if there are other observations below and above that kind of pull the same spring, one particular point is not going to have an impact. But if I'm all alone at the end pulling towards my end, okay, that's going to shift more. And so this point has a high leverage. But it's not an outlier. Why is it not an outlier? Well, if you look at the relationship, okay, maybe it seems like this is going up. I would have maybe wanted to have a slope slightly like this. But maybe actually all the observations, there's a lot of variability around the mean. And it would be reasonable to think there's also variability further up in the X. It's just that I have not seen large X values. On the left panel, I have an outlier. Why is it an outlier? Well, I said there's a mean model. Everyone pretty much follows the line, but you can see this value of Y, not X. Y is quite unusual. It doesn't fit the pattern. Now, of course, you can have both an outlier and a point with high leverage. If that happens, we're in trouble. So how am I going to look to detect this? Well, we're going to look at a measure called Cook distance. And essentially, it says the following. I'm going to look at how much the fitted values change when I remove one observation. So I get my model with all observation, I get my fitted value y hat. I repeat the same thing, and again, you don't need to refit the model, but now excluding that observation, calibrate the model, get the fitted value, get the estimates, beta hat -1, -I, get the fitted values for everyone, including the observation I had left out. And then I compute a measure of, the distance between the predictions, square, and I standardize this by the variance and the number of observations. So this is a square, this is a square, and that gives me what we call CI. So that's the Cook distance of observation I. How much did overall the predictions change when I, left out observation I? Again, you don't need to refit the regression. There is a wonderful formula for leave one out in terms of, again, the leverage. And here you see that crep dot, I have the externally studentized, or the jackknife residuals that have also crept in. So this Cook distance will be large in either of two settings. The first one is when the residual is large, that's typically an outlier, or if the leverage is high, or if they're both high, okay? So points with high Cook distance are going to be suspicious. We're going to want to have a further look at this. So what do you need to remember or keep in mind? So there's this H matrix. It has some properties, okay? But essentially, it's really the fact that the way we've defined the model, we kind of have our best guess. So the residuals, our best guess of the errors, but they're a byproduct, okay? Because they're constructed using an orthogonal projection matrix, they are uncorrelated with any of the regressors and the fitted value, because the fitted value is a linear combination, again, of the columns of X. That means that I can use this orthogonality to look for patterns. Second is the residuals, the way I've defined them, they are heteroscedastic. They have different variance, okay? And so I will want to compute different quantities, the studentized residual, to look at apple-to-apple comparison, okay? I can also look at what impact an observation has, how much does it affect the fit, and try to detect outliers, okay? So the studentized residual can be useful to detect outlier. The Cook distance can be useful to check for points with high leverage, also an outlier. So these are all diagnostics that will be part of my model assessment, model checking, and graphical diagnostics. So that's all for today. Thanks for watching.